Hi guys, welcome back. So we are looking at two more tests today for convergence and divergence, the direct comparison test and the limit comparison test. I don't like to play favorites, but if I did have to say I'd have a favorite, it's probably these two tests. Probably the limit comparison is my favorite. All right, because the P-series is just too easy to be my favorite. All right, so let's see, the direct comparison test. So let's see, we've got some series or some sequence AN and BN. If BN converges and B is greater than A, then AN converges, the sum of AN converges. So if the bigger one converges, the smaller one, the one that's below it, is always going to have to converge as well. All right. If the smaller one diverges, then the bigger one is also going to have to diverge. Like you think about it this way, like we've got some smaller one and its sum is going to diverge. So that means the bigger one, the one that's over it, doesn't have any choice. Like it wants to go down, but it can't go down. It has to keep going up, so it's going to have to diverge as well. All right, the other thing that happens is if AN does converge, or I guess we'll call this BN. If BN does converge, it ends up going to some number, and AN's less than it, well, it can try and go up, but it can't quite get over, so it's going to have to converge as well. All right, so that's, I always kind of picture that in my head when I'm doing this. All right, so converge or diverge? Well, let's try and compare this to something. Let's see, what if we just took out the troublesome area down here? Because if we took out this plus 2 here, then it wouldn't be a problem. Like we can compare this to 1 over 3 to the n, which is really just 1/3 to the n. All right, so how does this compare to this? Well, if we add more to the bottom, it makes it smaller. So this is less than this guy. And if we look at the sum of 1/3 to the n, that's a geometric series where r equals 1/3, which is less than 1, which tells us it converges. So if this guy converges and this guy is the bigger one, that means the smaller one here also converges. Neat, huh? All right, the other way around. So this guy looks like he's similar to 1 over, just say, the square root of n, which is 1 over n to the 1/2, which is a p-series, and it diverges. But which one of these is bigger? It actually turns out that it goes that way, that this guy is actually going to be a little bit smaller because that plus 2 down there. So what if we get something that's even going to be smaller than that? What if we took, like, instead of the square root, what if we took like the 3rd root or the 4th root? That would surely make it smaller than this, right? Nope, that wouldn't work. What if we did the other way around? What if we compared it to like 1 over n? All right, so at a certain point, n is going to be bigger than that, right? Because n will be greater than 2 plus the square root of n for, I wrote 2 again. For n greater than, let's see, does it work for 1? No. Does it work for 2? No. Does it work for 3? No. Does it work for 4? Yes, 4, they're equal to each other. After 4, they're fine. So for n greater than or equal to 4, the n's going to be bigger than that guy. All right, which means that 1 over n will be smaller than 2 plus the square root of n for n greater than or equal to 4. All right, so really, we don't care about the first couple of terms. The first couple of terms doesn't mean anything as far as what's going to happen when converge or diverge. We can just write out the first couple of terms and then just say that this is the sum from 4 to infinity with, you know, a1 plus a2 plus a3. And those first 3 terms are not going to determine whether it converges or diverges. But after this, this guy is bigger than this guy. And we know that the sum, so this didn't work for us. We know that the sum of 1 over n diverged. It's the p-series with p equal to 1, right? So that means this guy here that's bigger than it is also going to have to diverge. So that means this guy also diverges. All right, direct comparison test. It's okay. My more favorite one is the limit comparison test. So let's take a look at the limit comparison test. And let's change some colors here. All right, so suppose a sub n is greater than 0 and b sub n is greater than 0. So we have 2 different sequences or 2 different series. And we look at the limit. It doesn't really matter which one goes on top. But if the limit equals a number, a finite positive number, then both of them will do the same thing. They'll either both converge or they'll both diverge. All right, so this guy. So we have 1 over an plus b, where a is greater than 0 and b is equal to 0, or greater than 0 as well. So it's positive, that's what we're saying. We're taking care of the positive case. Let's compare this to just 1 over n. Because like really, we get rid of the b, we get rid of the a, it is just 1 over n with some dressing on it. So if we take the limit as n goes to infinity of, again, doesn't matter which one goes on top, like that, that'll be n over an plus b. We end up getting 1 over a, right? Because this is roughly n over a sub n, which gives us 1 over a as we go to infinity. So this is a number, right? We're told a is just some number. So that means these two series do the same thing. This one diverges. So that means this one also diverges. All right. And now what ends up happening is we really just have to look at the largest degree term on the bottom and just compare it to that. Well, so we can compare this to 1 over n squared. And then if we do the limit comparison test, the LCT as we sometimes call it, not CLT for those of you in stats, as n goes to infinity of 1 over 3n squared minus 4n plus 5 over 1 over n squared is going to be n squared over 3n squared minus 4n plus 5, which as we go to infinity will just be n squared over 3n squared, which gives us 1/3, which is a nice whole number. And this one is a p series where p equals 2, therefore it converges. That means this guy will also converge because we can compare it to a p series with p equal to 2. All right, so now you should be able to do the same thing for this last one here, probably in your head, just thinking the limit comparison test. Because what does this compare to? Well, it compares to 1 over the square root of n, which is 1 over n to the 1/2, which diverges by the p series. All right, so if we do the actual limit now, as n goes to infinity, of 1 over the square root of 3n minus 2 over 1 over the square root of n, we get the square root of n over the square root of 3n minus 2. So this is, as we go to infinity, it's really just the square root of n over the square root of 3n. So we end up getting 1 over the square root of 3. So that means this guy will also diverge because this guy diverged. All right, limit comparison test. It's a very useful one with any sort of polynomial functions or radical functions. Limit comparison test is probably your best friend. All right, so here's a bunch of different tests that we've looked at so far. So the first one here, we got something with n on top, something with n on bottom. If we looked at the highest power on top and the highest power n on the bottom, we could say that this is 1 over n to the 3/2, roughly. So we can use limit comparison test with the sum of 1 over n to the 3/2. All right, and if we do that, that limit will equal 0. Or not 0, actually, that limit will equal 1. All right, with this over that. And this guy converges. Therefore, that guy also converges. Done. All right, if we just move right along, this guy, let me just try, one of the first things I like to try is just the nth term test. And limit as n goes to infinity of n 2 to the n over 4n cubed plus 1. All right, so this is essentially n 2 to the n over 4n cubed. So one of the n's is going to cancel like that. And this is exponential on top, and this is not exponential down here. So this limit is actually going to go to infinity. All right, so remember, if we take the limit of this guy and it's not equal to 0, that means it diverges. So this is the nth term test. So That guy diverged. This guy was the limit comparison test, converged, nth term test, diverged. And we'll keep working my way down through my colors. This guy, oh boy. There's actually a couple different tests for this, but one thing I can note is, well, it's starting at 2. That's a little strange, but yeah, 1 would be a problem down here. 1 over n ln of n is definitely greater than 0. It's continuous. And the bottom's always going to keep getting bigger, so it is decreasing. Always. So I can do the integral test from 2 to infinity of 1 over n ln of n dn. And this is just substitution. We've done this integral before. All right, so we've got our u's on the bottom. So this just basically becomes the integral of du over u. So that's ln, the absolute value of u. And when u was the ln of n, so we get the ln, the absolute value of the ln of n from 2 to b. So this is the natural log of b minus the natural log of 2 as we go to infinity. So, natural log of the natural log of 2. Sorry, I left out an extra natural log here. Don't actually need all the absolute value bars, but whatever. All right, so this guy is going to go to infinity, which means that that integral diverges, which means that this guy diverges by the integral test. So ln of n added to, or multiplied on the bottom there times n is not enough to make that converge, but like n to the 0.00001 would be enough to make it converge. So ln of n is smaller than any n to any power kind of thing is what we're getting from that for positive powers. All right, next one. This guy, let's see, moving right on down the rainbow, green. All right, so this guy is of the form of a geometric series. All right, it's got some number raised to n. So that r is 3/4, which is less than 1. So that tells me that it converges. In fact, if we plugged in 1, we get 5 times 3/4 as our a, our first term, and our r is 3/4. So the sum here would be 5 times 3/4 over 1 minus 3/4. So it would be 4 times that, which is 3 times 5 over 4 is 15. So if we add it all up to all those terms, we actually would get 15. It's like the only one we can find the sum for. All right, and then this last guy here, I guess red's left. So we got something with n on top, something with n on the bottom. This is essentially n to the 1/2 over n to the 3rd, which is 1 over n to the 2.5. So by the limit comparison test, if we took these two limits, we're going to get like 1/2, right? Like 1/2 here, 1 here. So the limit comparison test, the square root of n over 2n cubed over 1 over 2n to the 2.5, limit as n goes to infinity, equals just this 1/2 is the only difference there. And this is a p-series that converges, because p is 2.5, which is greater than 1. So that means this guy also converges by the limit comparison test. I really like that limit comparison test. I mean, we could have actually done direct comparison for this one, but I just like the limit comparison one better. All right, and that is it for this one. So that is it for 9.2. So there's your homework. Yeah, it's there. So go take a look at your homework on Google Classroom.